Rotating current loop. A square conducting wire loop of side L, capital L, total mass M, and total resistance capital R initially lies in the horizontal xy plane with corners at 0, 0, 0, 0, L, 0, L, 0, 0, and L, L, 0. There is a uniform upward magnetic field in k-hat direction in the space within and around the loop. The side of the loop that extends from 0, 0, 0 to L, 0, 0, that's on the x-axis, is held in place. The rest of the loop is free to pivot around this axis. When the loop is released, it begins to rotate due to gravitational torque. Part A, find the net torque, magnitude, and direction that acts on the loop when it has rotated through an angle phi from its original orientation and is rotating downward at an angular speed omega. So here is our square loop. This side is fixed. It's going to rotate about this pivot, about this axis, and we can basically look at it from this point of view, so that the x-axis is coming out of the page and y and z-axis are in the page. When it has rotated through an angle phi, we will see that there's this magnetic field B pointing up, and there has to be an induced current on this loop. Why? Because the flux density, basically B, causes a flux in this loop, but that flux is decreasing as the loop rotates because of this angle phi here. So we need to consider B cosine phi. As phi increases, the flux is decreasing. So to oppose the decreasing flux, we must make sure that there is an induced magnetic field that is going to cause the same flux. So that is basically achieved by having the current flow in this direction, so that this current loop will create a magnetic field in the positive, in the k-hat direction as it comes down. So basically the current will be flowing in this direction, as you can see here. Okay, now there is the weight of this square loop, that's mg, that's pointing down, and that will exert a torque with respect to this rotation axis, and there is the magnetic moment due to the current that is induced in this loop, and that magnetic moment interacting with the magnetic field will create a magnetic torque. Okay, so let's think about these torque terms now. The first torque comes from the gravitational force. It is R cross gravitational force, Fg. R is the position vector of the point of application of the force with respect to the rotation axis, and that's basically this L over 2 here, because we're right in the middle of the loop. And so we will have L, capital L over 2. The gravitational force is mg, but we need to consider the perpendicular component of the gravitational force with respect to this r vector, which is mg cosine phi. So mg cosine phi. Now what is the direction of this torque? The right hand rule tells us if the four fingers of the right hand point in the direction of the r vector curled towards the gravitational force, the thumb points into the page. So this torque is in minus I hat direction. On the other hand, we have the magnetic torque. The magnetic torque comes from the cross product of the magnetic moment with the magnetic field, mu cross B. So the magnetic moment is the induced current times the area A multiplied by B. What is the angle between the magnetic field and magnetic moment? That is this angle phi. So this is sine phi in I hat direction. Using the right hand rule, mu cross B, four fingers of the right hand point in the direction of mu curl towards magnetic field. The thumb points out of the page in plus I hat direction. The flux phi b is BA cosine phi, which is the dot product of the magnetic field with the area vector, and the induced EMF epsilon is minus d phi b dt, the rate of change of flux, and that is basically because the angle here is changing, BA sine phi d phi dt. All right, and therefore the induced current I will be equal to the induced EMF epsilon divided by the resistance of the loop, which will be the induced EMF is B times the area, which is L squared because it's a square loop. Sine phi d phi dt is precisely the angular speed omega divided by the resistance of the loop R. So as the loop rotates, the magnetic flux decreases. So that's what we see. Therefore, current is induced in which direction? Clockwise direction. So looking from the top here, I should see that the current flows in counterclockwise direction, sorry. So the current should flow in this direction, which is looking from the top, counterclockwise direction. So in counterclockwise direction, to generate an induced field that opposes the decreasing flux in the direction of the magnetic moment vector mu. Okay, so that's basically this direction that I'm showing here. All right, so this is going to induce a magnetic field in the direction of mu. So that's going to make sure that the flux here is, the decrease in the flux is compensated for using Lenz's law. Okay, so what is the net torque acting on this loop? There is the magnetic torque, I is B, capital B, L squared omega sine phi over R. I multiplied by area is L squared, and then we have magnetic field B and sine phi. So we have B sine phi, and this is in I hat direction. And then we have minus the gravitational torque L over 2 mg cosine phi. Capital L over 2 mg cosine phi in I hat direction. So if I rewrite this, taking into account that this is L to the fourth power, this is B square, etc., I can write the net torque. Let's take it here. Okay, so we can now write the net torque as B square, capital L to the fourth power, omega sine square phi divided by R minus the gravitational term mgl cosine phi divided by 2, that is this term here, and this is in I hat direction. So that's the net torque we obtain for part A of the problem. Okay, now let's move on to part B. And here I should note that the torque acts in the opposite direction of the angular velocity omega. What's the direction of angular velocity omega? Using the right hand rule, the four fingers curl in the direction of omega. Angular velocity is in minus I hat direction. So that's basically, this is in plus I hat direction, in opposite direction of omega. Let's move on to part B. Find the angular acceleration of the loop at the instant described in part A. Now, angular acceleration is related to the net torque. Newton's second law, rotational form. Net torque is moment of inertia I times the angular acceleration, where this I is not the current, where I is the moment of inertia the moment of inertia, and with respect to x-axis rotations. The rotation axis is the x-axis. Okay, now if I look at my square loop here, this is the x-axis, and that's around which we are rotating, and this consists of 4 segments, each with mass m over 4, because of symmetry. First segment, second segment, third segment, and the fourth segment. So if I consider the moment of inertia, let me calculate the moment of inertia for these rotations. For segment 1, the mass element dm has a mass which is linear mass density lambda times dy because it's on the y-axis, and the mass density here is the total mass m divided by the total length 4L, m over 4L dy, and therefore the moment of inertia for the first segment will be integral as y goes from 0 to L, y square dm. It's integral r square dm. So the moment of inertia for the first segment is m over 4L, integral from 0 to L, y square dy, and because I'm at a distance y here from the rotation axis, this is going to give me m over 4L, y cube over 3, which is L cube over 3 when evaluated between 0 and L. The answer is ml squared divided by 12. Now, similarly, if I consider segment number 3, I would have the same scenario here. So I can say without any further calculations, similarly, the contribution from the third segment is equal to the contribution from the first segment, which is ml squared divided by 12. And for segment 2, I have to do a calculation. For segment 2, we have a constant distance, that's basically L. So the moment of inertia for segment 2 is very easy. It is its mass, m over 4, multiplied by distance squared, L squared, which is 3ml squared divided by 12. So if I calculate the moment of inertia, which has contributions from segment 1, segment 2, segment 3, and segment 4, this will be equal to ml squared over 12 plus 3ml squared over 12 plus ml squared over 12 plus 0, because that's the rotation axis. So we have 5 over 12 ml squared. So that's the moment of inertia. Now I'm ready to write net torque is equal to moment of inertia times the angular acceleration alpha. Then I can write alpha to be 12 over 5 ml squared net torque divided by moment of inertia multiplied by the net torque we calculated in part A, b square L to the fourth power omega sine square phi divided by R minus mgl cosine phi over 2 in I hat direction. So if I simplify this a little bit, I find the angular acceleration b square L square, because this is L to fourth, this is L squared, omega sine squared phi divided by 5 mr minus 12 divided by 2 gives me 6. 6 masses disappear. These two masses disappear. So I have 6g cosine phi. Also, I get rid of one of the L's here. So I have one L remaining at the bottom divided by 5L in I hat direction. So that's the angular acceleration I'm looking for in part B. Now let's move on to part C. Compared to the case with zero magnetic field, does it take the loop a longer or shorter time to rotate through 90 degrees? Explain. So if I look at this situation with zero magnetic field, then I would only have the torque due to gravitation, but you can see that this interaction between the magnetic dipole here, magnetic moment, and the magnetic field causing a torque in the opposite direction, this will try to slow it down. So since the magnetic torque opposes the gravitational torque, it takes longer. Okay? And in part D, is mechanical energy conserved as the loop rotates downward? Explain. Well, part of the energy is lost. How is it lost? It is lost to resistive heating. Resistive heating at a rate PR is equal to I square R. So mechanical energy is not conserved because part of the energy is lost to thermal energy. It's basically converted to thermal energy, so it is lost irreversibly. Okay, so in this problem, we have a square loop that is on the xy plane initially, and you can see that the center of mass is right in the middle. And looking at it from this point of view, x-axis is coming out and y and z-axis are here. The magnetic field is in plus k hat direction. The loop starts rotating due to the gravitational force mg pointing down, there is a torque here, L over 2 times mg, which will try to rotate this loop. And as it rotates through an angle phi, because the flux through the loop, which is BA cosine phi, is decreasing as the angle increases, there is an induced current that will try to produce a magnetic field in the plus k hat direction initially, or in the direction of the area vector or magnetic moment vector in this case. So this current will be flowing in this direction or in this direction. Then there will be a torque mu cross B, which is going to try to rotate this in the opposite direction. The gravitational torque is R cross with Fg, the gravitational force mg pointing down. Mg cosine phi is perpendicular to the R, the position vector of the point of application of the force with respect to the rotation axis. L over 2 mg cosine phi in minus I hat direction. So R cross F, using the right hand rule, 4 fingers curl in this direction, the thumb points into the page, minus I hat. The magnetic torque is mu cross B, which is IAB sine phi, because phi is the angle between B and mu, in plus I hat direction using the right hand rule. And the induced EMF here is minus d phi b dt, which is BA sine phi d phi dt. And the induced current is epsilon divided by R, the resistance of the loop. So it's going to be BL square sine phi omega divided by R. And I is induced in the counterclockwise sense. The net torque is the sum of these two terms. So we have I area A, B sine phi, minus L over 2 mg cosine phi I hat. That's the net torque. The net torque is equal to moment of inertia times angular acceleration I alpha. So here I have calculated moment of inertia by using the definition. The moment of inertia is integral r square dm. So remember that we have, we can recall this from basic mechanics class. I is equal to integral r square dm. So r is the distance between the mass element and the rotation axis. So here it is y, so I take a dm here, which is, because it's a loop, it has a mass density lambda, which is the total mass divided by total length for L. And for each segment, I calculate moment of inertia. For segment 2, it's very easy because the distance for each mass element is basically L. So m over 4 times L squared is the moment of inertia. But for segments 1 and 3, I have to do this integral m over 4L y squared dy from 0 to L to cover all mass element contributions. And the total moment of inertia is 5 over 12 ml squared. So net torque divided by the total moment of inertia gives me the angular acceleration alpha. The magnetic torque is opposing the gravitational torque. So if we didn't have this magnetic field, it will take a lot less to come down. So with the magnetic field being present, it takes longer for the loop to make its 90-degree turn here. And because in this process, the induced current flowing through the loop encounters this resistance R, there is resistive heating I square R. So part of the energy is lost to resistive heating. So we cannot talk about conservation of mechanical energy in this problem.